Hey there, chemistry team. You ready for one of the weirdest of all lectures? There's some weird ones, but this is probably up there in the top two or three of total weirdness factor. The wave mechanical model. So let's just kind of review what we've been building up. We're building up a story, building it up, building it up. People are throwing these ideas and talking about this and that. Massive brain power in the early 1900s, quantum mechanical revolution. So we got de Broglie, right, proposes electrons as a matter wave. Weird, but proven, right? They underwent diffraction. Heisenberg, the electron's not a point particle. It's spread out region, right? You can't precisely locate it. It's spread out negative charge. What? Okay, so we can't really find it exactly. What do we do with these ideas? All right, well, finally we have someone who takes all the puzzle pieces and puts the puzzle together. Erwin Schrödinger. Note the umlaut Sch. I remember when I was in college choir, we would sit there and just practice. We would sing, songs in German sometimes. We'd sit there for like 10 minutes one time practicing everybody how to say an umlaut Sch. I don't know if I say it right anymore, but anyway, that was hard. So anyway, 1927 is starting to culminate all together. Still took some refinement, but finally someone was able to take these ideas, take Bohr's model, which worked great for bridging classical and quantum ideas. It worked only for one electron species. So Erwin Schrödinger now was able to upgrade, right? It's almost completely different, but kind of upgrade Bohr's model of the atom and electrons moving as point particles in classical circles. Wrong, not right. And he was able to now look at an electron as a wave, as a matter wave, that you can't precisely locate. So he put together this upgraded model of electron motion, electron energy. It's called the wave mechanical model, right? Mechanical, you think of it as mathematics and wave behavior. So we know, that he was an expert in wave mathematics, okay? So now we have this special type of view of the electron. Let's take a look first at the different kinds of waves. There's a specific type of wave Schrodinger's going to treat an electron as. Then we'll kind of summarize. I'm not going to do the gory stuff. I don't want heads to explode, but I'll just kind of show you a synopsis saying, hey, he went from here to here to here, maybe 3 or 4 main points, but I'm not going to go through a lot of the gory detail. If you want to do the gory detail, you can take physical chemistry or PChem or graduate level quantum mechanics, right? Or you can, read on your own. You can, open up the door, go down the rabbit hole as far as you want, my friends. That's you on your own time. All right, our two types of waves, which you're probably familiar with, traveling waves and standing waves. So typically most people, when you mention a wave, they think of a traveling wave, right? A wave, you're standing on the beach at the ocean, you see the waves traveling across the ocean, you take a light, shine it up in outer space. Ooh, how far will it go, Dad? Or forever till it hits something. But that's a traveling wave. There's no defined boundaries. It's not constrained in any way. Whereas a standing wave, it's still a wave. Remember, we're going to treat electrons like waves, but it's got a distinct starting point and a distinct ending point. We're forming boundaries, right? Kind of like we talk about, like a guitar string. If you pluck a guitar string, or if you're with your friend, you got a jump rope and you start going, or I see people at the gym, right? There's a real popular thing where they got this big thick rope that's tied on one side and you grab it and you're going, it looks really painful. I refuse to do it. And they're like, oh, my arms are so exhausted. But I see the wave on the rope, right? That's going, but it's constrained. So what happens with that wave, it travels, hits one end, and then goes back and forth on itself. So I'm going to show that on the next board. But now this is my daughter's. I don't play guitar. I was a drummer. The notes were all the same. They didn't go up and down. And then I was a singer, but I never knew how to read notes. But with the guitar, you can see how it's constrained, right, on one end here. And wherever I put my finger, right, wherever I put my finger, or this note or something, right? So you get, when you pluck it, you get a particular wave set by the boundaries of it. So if I move my finger, right, I can get different things. I don't know how to play at all, so it's embarrassing. But if I move my finger, I can change the allowable wavelengths or frequencies, and you get a different sound, right? Because by moving my finger, I'm changing the boundary. That's a standing wave. Let's take a look at what that standing wave is. Nobody's played this. There's dust all over this thing. What's the point in even buying a guitar if nobody uses it? let's draw a standing wave and show you some of the mathematics and the constrained boundaries create a quantum situation. Oh. All right, simplified view of plucking that guitar string. Wow, bring it up here. So here's one end of the guitar string, right, where it's set, and here's where my finger goes. So that creates a length, right? Let's call that capital L. That's the length of the boundary that's now constrained. And if we have that wire and pluck it, then it undergoes vibration, right? So these are going to go up and down. Right, so you get this oscillation. So you go one, one, one. That's going up and down, with set amplitudes at each point. So this is here, and then it goes down to here, and then up again, blah, blah. So it creates kind of a region where, kind of like a hummingbird wing, right? You can see that the string, if you could really look at the string's going up and down so fast, it just looks like a blurred out region. Oh, kind of like a smeared out electron. Oh, yeah. And you get these points where there's no displacement at all. Right? It just is set there. So obviously at the boundaries, there's no displacement. They can't go up and down. And then depending on the wavelength, you might get a node or two nodes or three nodes. Just a node's just a region of zero displacement. We'll see that later as a place where the electron can't exist. At that point, there'll be no electron charge density there. So in order for this to work, right, the waves, imagine a wave traveling and then moving back on itself. So it goes boom, 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 and it can constructively or destructively interfere. So there's only specific wavelengths, integrals of the length, where the wave can be in phase going back and forth and not consume itself, right? All other wavelengths will destructively interfere and that wave cannot exist. That's why you get set frequencies or tones. Wavelength, frequency, you can think of them, they're just inversely proportional, right? That's why you hear certain sounds where you put your finger. But then again, I'm not a guitar player. So that wavelength, if you look at the mathematics, right, this is just known wave mathematics, the wavelengths that can exist and be in phase going back and forth is 2 times the length of the boundary, we'll call that a box, divided by n, and n is some integer 1 or greater. So it could be 1 or 2 or 3 or 4. So they'd be integrals. So for example, this one, n is equal to 2, right? So 2 divided by 2 is 1, so the wavelength is L, right? That's one wavelength, right? And you could put, and if n was 1, it'd be 2L, right? So you could, but you only have specific values of wavelengths because of the constraint on the value of n, where the wavelength doesn't consume itself by destructive interference. Only certain ones exist. This is also going to be true when we look at electrons in 3 dimensions. We'll stick with just 1 dimension for now, and then just say, poof, this is what happens when you go to 3 dimensions, all right? So let's actually take a look at that, more of an electron. Let's again, stay away from the 3 dimensions, but let's transcend the standing wave to an electron, kind of in a like a Bohr orbit. Let's kind of overlap this wave model with the Bohr model a little bit. All right, this should give you kind of a simplified view. Bohr orbits are a little kind of easier to grasp in our macroscopic thinking brains, right? But instead of viewing the electron as a point particle like Bohr did, moving around in concentric circles classically, let's look at it as a standing matter wave, right? Thank you, de Broglie. Electrons are matter waves, but specifically standing matter waves. This is how Schrodinger is going to treat an electron mathematically later when we look at Schrodingers Equations, blah, 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 right? So here's 2 scenarios. One where the wavelength of the electron wave actually is allowed, and one where the wavelength of the electron wave is not allowed. So this will constructively interfere and destructively interfere. This one will destroy itself. This one can exist. So if you start the wave here, right, it goes around with a certain number of wavelengths based on that equation we had before, where n is 1, 2, 3, 4, 5, etc. So as it comes around, kind of like a snake eating its tail, it comes around and ends up in phase with itself, so it can just keep going and going and going. So that's an allowable wavelength. So that electron wave can exist, and that'll have a specific energy we can calculate using wave mathematics, wave mechanics. Whereas here, if we have an electron wave with a non-integral wavelength that doesn't match that equation, as it comes around, it comes back, but it's out of phase, right? So it's out of phase. It doesn't give you a really nice in-phase reattachment to itself. So what will happen is as it moves around, it destructively interferes with itself, and it can't exist. Hopefully that, not the most super accurate way of looking at it, but I think it gives you a good macroscopic brain way of going, oh, that works, that doesn't. So we'll find out certain distances from the nucleus where that it doesn't work. an electron can't exist, and certain distances from the nucleus it can't, kind of like the Bohr orbit as well. But we're still not quite thinking three-dimensionally. So let's advance this a little bit. Let's take a small peek into Schrodinger's brain. No! All right, to get into Schrodinger's mind, let's take a look at the basic mathematics of a standing wave trapped in a box with defined boundaries. They call that, you'll hear this all the time in quantum mechanics, you'll always start with the particle in the box. I'm going to skip a lot of the gory mathematics that you would do at higher levels. Just kind of get the basic qualitative look. So I'm not going to derive the equation for you. So again, this is a mathematical treatment of waves, standing waves, trapped with boundaries on either side. It's a standing matter wave. And we're going to treat electrons. Schrodinger's going to treat electrons mathematically using these mathematics. So the motion, the wave motion of that standing wave is treated with what's called a wave equation, right? So they use the term psi, and we're just looking at x. We're just looking at a wave in one dimension. We're not looking at y and z, right, in Cartesian coordinates, just one. So we'll have to account for motion in the y and z axes later. We'll actually go to polar coordinates probably later. Sorry for swearing. So that wave function, not deriving this, if you want to look, you can dig down that rabbit hole if you want to, but it's a little easier to understand if you've had differential equations, right? Some calculus. So I remember when I was in undergrad, I took Calc 1, algebra, trigonometry, Calc 1, Calc 2, Calc 3, and then I took differential equations. As an elective, like a dummy, I could have taken archery or something. That would have been so cool, but no, my senior year, I had one more. I had two electives in the college. I was like, anything you want. One I took, it's like soft shoes dance or some kind of like dance class, because my friend talked me into it. And then I took differential equations. Oh, it was really one of the hardest classes I ever took, but it was really intriguing because I got to see where a lot of equations were derived, how they were derived, equations I used in chemistry, and how they came about. It was like, opening up the hood and looking underneath. It's kind of cool. So I'm not going to show you where this comes from, but if you want to look into it, go for it. You're welcome to. But this is the result of it. So that wave function for just the x-axis in one dimension is the square root of 2 over L, the length of the box, right? So we're going to set the boundaries, right? Moving our finger down the guitar string, boing, 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 increasing L, boing, 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 boing. Actually, boing, 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 as it goes to a lower frequency. Sine of n pi x over L again. And there's n, there's your quantum number. So n can be 1 or 2 or 3, those kinds of things, right? I'll put that. So n can be 1, 2, 3, dot, 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 dot. Can't be 0. X direction, pi. Now, I'm not going to get into the details. Why is it sine versus cosine and stuff? You need to use a sine function because that allows you to get nodes or points of zero motion on the beginning and the end point. If you use a cosine function, it doesn't. That's neither here or there, but the sine function works. That's why you see sine all the time. It's a sign of the times. So let's take a look. Now the number of nodes is n plus 1. Okay, so let's say we have n equals 1. All right, so if we put an n equals 1 solve for it, we get 1 plus 1 or 2 nodes. Well, that's the 2 boundary points. Woo! So you get kind of a half a wavelength in there that can exist, right? If n equals 2, so that call that psi 1, allowable wavelength 1. Let's do allowable wavelength number 2, right? So if n is 2, 2 plus 1 is 3, so you get the 2 boundaries plus a node right in the middle. So you get 1 full wavelength that goes back and forth and is in phase with itself. Anything in between would destructively interfere. It doesn't work, right? So can you start to see where electrons are quantized? What I'm gonna do is translate this into electron energies on the next board. But I want you to see why only certain wavelengths are allowed. And then if n equals 3, well, 3 plus 1 is 4. We'd have 4 nodes, right? So the 2 n's plus 2 in the middle. So you get the 1.5 wavelengths in there. Right, so this is the traditional particle in a box. And if you take PChem or graduate level stuff, you have to solve for this stuff, right? Derive that, solve for it. So you need to be heavy in calculus. I highly recommend you take differential equations. Highly, highly recommend it. All right, so let's take a look at how the result of energies from this, and then we'll take it how Schrodinger treated an electron, and Schrodinger solved these equations. So smart! And let's see what we get as a result of those solutions. It's going to give us what you're familiar with as orbitals, not orbits, not those circular orbits that Bohr talked about, but the solution to the wave mechanics that Schrodinger did is called orbitals. Real weird. Feel free to derive this on your own if you're bored on a Saturday morning or something. Got nothing to do, stuck in your house, 105 degrees Fahrenheit outside. Note I put my unit of my temperature. Always give your units, right? Too hot to go outside. What are you going to do with yourself? Are you just going to play video games all day? Binge Netflix shows? Or are you going to derive the quantized energies from electrons of standing matter waves from a particle in a box? Come on! What is more fun? All right, even I skipped it. Now, I could have done it, but I don't want neurons to go pop, 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 pop. But if you're really interested, deriving stuff is kind of fun. It's just a bunch of sequential algebraic substitutions. You can do it. You can do it. So we all know this, right? Kinetic energy, 1/2 m. Well, I'm so used to V from physics, but for some reason, a lot of times in chemistry, they use U for velocity. So 1/2 mass times velocity squared. Well, you know momentum, P, is mass times the velocity, correct? So you can play around with this and incorporate the momentum into there. And then we know from de Broglie's equation, the wavelength of a particle wave, right, is Planck's constant over mass times velocity, but mass times velocity is momentum. So really the wavelength of that electron particle, or particle in a box in this case, is Planck's constant over the momentum. Thank you, Louis de Broglie. And we know from the original setup of a particle in a box, we've got restricted or quantized wavelength values that are in phase. All the other ones destructively interfere. And that was equal to 2 times the length of the box, right? Where do you put your finger on the guitar string? Divided by n. There's the quantized nature. N can be 1 or 2 or 3. So if you play around with that and do the algebraic substitutions from de Broglie and the allowable wavelengths from the quantum mechanics, you end up getting the kinetic energy of the wave, that standing matter wave, as n squared times Planck's constant squared over 8 times the mass times the length of the Z box squared. Note n. N can be 1, 2, 3, 4, 5. It's quantized. That means the energies are quantized, right? The wave energies can only be specific values, which means if we treat an electron, or if Schrodinger treats an electron as a standing matter wave, the electron energies are quantized, which helps describe and explain atomic line spectra, which was what Bohr tried to do, all that cool stuff, right? Goes back to Max Planck and Einstein. It's awesome, right? Now note, n cannot be 0. If the minimum value of n is 1, the kinetic energy of the electron cannot be 0, which means the electron can never just be sitting there. I'm just sitting there, not doing anything, right? That can't happen based on the quantum mechanics here. The electron minimum value of energy is n equals 1. So electrons have to be in motion. They cannot be at rest. All right, so they call that the 0, if n equals 1, they call that the 0 point. It's not 0 energy, it's the 0 point energy. It's the lowest energy that can be allowed. All right, now that we know the particle in the box mechanics, let's see how Schrodinger took this and actually applied it to electrons in hydrogen atoms, or hydrogen-like species with 1 electron only. All right, some qualifications before I melt your brain with Schrodinger's equation. I'm actually going to write it for you. There's a simplified form that most people write. I'm actually going to show you the whole thing so you can vomit profusely all over your video camera and whatever you're watching this on. And then I'll just say we're never going to use that, and then do the actual one that most people use. So anyway, so he solved the wave equations for hydrogen and hydrogen-like species, meaning 1 electron, right? The only difference being Z, the atomic number, or the nuclear charge that electron feels. And he did this in 3 dimensions. Everything I did before was 1-dimensional particle in a box. The energy was for 1 dimension. Try doing that in 3 dimensions. Yikes! Which means there's a couple coordinate systems you can choose to use. So he treated an electron as a standing matter wave. Thank you, de Broglie. Thank you, Heisenberg. In 3 dimensions. It's a lot more complicated. And because there's 2 coordinate systems, so I think originally he did the X, Y, Z, which is traditionally how most of us think, the Cartesian coordinates, X-axis, right? Got X-axis, Z-axis, and the Y-axis coming at your face, depending on how you rotate it. I forget what it was. Max Born. I can't remember. Somebody convinced him to do it in polar coordinates. I'll show you the difference between Cartesian and polar. Not the end of the world, but polar coordinates, instead of locating it, like say it was a particle in 3 dimensions, x, y, and z, you use from the center a radius and then 2 separate angles. Right? 2 separate angles. Let me show you what that looks like, and then I'll show you Schrodinger's equation, the real one, so we can hurt our brains, and then the summarized version, which is what we're never gonna solve for it, so you don't need to know the equation. I just want to show you how crazy it is. I hope you didn't just pass out. Oh my God, we are never going to use this in my class, like ever. A lot of times I don't even show it. I just wanted to put this up just so you can see how complex this stuff actually is. This is the solution to just one electron species. Oh my goodness. Of course, the Z value's in there if it's, something that's hydrogen-like species. But here's the 2 different coordinate systems. Again, I just want you to comprehend the difference between them. Of course, the X, Y. Commonly, I put X there and Y there, but it just depends how you label it. Z going up. So that would be your traditional Cartesian coordinates, X, Y, Z. Polar coordinates, if we're locating, say, this red dot here, well, from the center, there's a radius. See that? And if there's an angle from the Z-axis here, I think is that theta? Got to work on my Greek stuff, man. And then if you bring this down, it's actually coming in between the X and Y axes. And so you can see this other angle from the X-axis here. Can't remember what that is. So with these 2 angles and the radius, you can locate this point 3 dimensions, just like you could with X, Y, Z coordinates in the Cartesian coordinates. So polar versus Cartesian. So we solved it in polar coordinates. And this is what he got, all right? I just look at it. I'm not even going to explain this to you, but you get all these, here's your wave function. You get all these differentials, and you got an energy here. You can see the radius. You can see the different angles that are in here. You can see the sine function for the wave. So, you can get bits and pieces of it, but I know this is just going to create massive gastrointestinal disorders, diarrhea, vomiting, maybe some venereal disease. I don't know, but we're not going to solve. If you want to take graduate level quantum mechanics, you can solve for that. Okay, my friends? Maybe if you get a P-Chem professor that's going cuckoo on you, rock and roll. So what we're going to do is we're going to summarize. You okay if I just summarize this down? Let's take this whole mess and call that H, a Hamiltonian operator. Oh, Alexander Hamilton. We'll call that H psi equals E psi. This is the familiar form. So when I passed physical chemistry, made shirts, burned holes in them, and just put horrific equations like this, and it says, I survived P-Chem. Physical chemistry was one of the hardest classes I ever took in undergrad college. It was calculus-based and brutal, all right? But it really dug into it. So anyway, I just wanted to show you, holy guacamole, man. That's some crazy stuff. So let's talk on the next board. What does it mean? And that'll lead to this concept called orbitals. All right, let's take a look at this wave function. Before we get into orbitals. So we're looking at electron energies and electron location, but how do you locate a smeared out wave, right? So in the quantum view, right, when we're looking at an electron, the wave function itself doesn't have a lot of physical meaning of where the electron is, because you got a wave, right? And you got a positive and negative, goes up, goes down, positive, negative. So what you'll see is if you square it, if you work through the mathematics, if you square the wave function, what happens? All right, so let's take a look at this if I square this. Remember, if you square a negative, negative times negative is positive, so you don't get the positive negative anymore. So if I square this wave, so this is the wave function for, I think it's n equals 1, no, that's n equals 2, I think, in the x direction. Let's square it, and what happens? You get this. See that? Oh! Imagine that's lined up with that, right? But that squared becomes this. So now you get this region of where the electron is spread out, smeared out, likely to be. They call that the electron density map, right? Or electron charge density, how that electron charge is smeared out. Thank you, Heisenberg, for that one. So psi squared, the wave function squared, describes the electron charge density, or what you'll commonly hear, the electron probability density. So if they say, hey, where is that electron located? You'll say, somewhere in there. Right? It's pretty weird looking. So you get these electron probability distribution maps. And what Schrodinger does, and we're going to do this on another video, we're going to show you the results of the solutions to the Schrodinger's equations, where you get these three, and this is just one dimensional. Imagine doing it in 3 dimensions. You get these characteristic shapes in 3 dimensions that encompass the electron probability that's spread out over space. We call those orbitals. Let's do that on the next board. And then this video is getting pretty long. We'll look at, we're going to have to look at quantum numbers, how we characterize these. And then we'll look at the actual shapes. This is going to take several videos, my friends. All right, last board for this. Then we'll get into some other juicy stuff. So Schrodinger's solutions, right? He solved for the 1 electron species, whether they're hydrogen-like or hydrogen, for the electron wave functions in 3 dimensions. Remember, we've been looking in 1-dimensional only, the particle in the box, 1 dimension. Tracking that to 3 dimensions, where I gave you that full Schrodinger's equations in polar coordinates, 3 dimensions. Solving for that, for n equals 1, n equals 2, blah, 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 gave electron density distribution maps, I guess you could think, which shows that spread out electron charge. So what we do, and they spread out, right? So what they do is they cap it. And I've seen people I've seen some textbooks where they cap it at 90% of the total electron probability. Some do 95%, whatever's used, right? I'll just use 95%. So what we do is we just take that electron density, right, this distributed charge, and just draw a boundary, and inside that boundary contains 95% of that electron density charge, or 95% of the electron probabilities in that particular 3-dimensional shape, right? That probabilities in there. That's what they call an orbital, not an orbit. The Bohr orbit is that circle that he treated, which was completely wrong. So this is kind of the improved version called an orbital. It's a 3-dimensional shape that contains 95%, sometimes 90% of the electron probability or electron charge density. And boy, do you get some crazy shapes, my friends. Now, when we did it in 1 dimension, we had the quantum number n, correct? N could be 1 or 2 or 3. But once we go to 3 dimensions, I wonder how many quantum numbers we need now. 3 dimensions, 3 dimensions. Oh, it says it right there. 3 quantum numbers. Oh, so let's do that in the next video. We'll talk about quantum numbers and how to characterize these orbitals. And then that'll probably be too long on itself. We'll do another video that actually shows these shapes of these crazy things called orbitals. Yay, quantum mechanics!